So let's take a look at this problem. It says, in the following exercises, evaluate the iterated integrals by choosing the order of integration. So we're just going to evaluate this one the way it sets, and we'll see how this works out for us. So we have 0 to 1 here, and then we have the integral from 1 to 2 of x e to the x plus 4y dy dx. Now for this problem, there's a lot of noise here. What I mean by that is if I'm going to do dy first, I have this e, this x, and this plus 4y, when actually I can pull out a constant here. And this constant might not be apparent to you, but take a look at this. So that's 0 to 1. I can pull out an x, e to the x, and they have the integral of e to the 4y dy dx. Now take a look at this. Before I pull the 2 out here, I want to show you why this is okay. So if I take x e to the x and I times it by e to the 4y, now I have the same base here and here. So in general, what do I do with my bases when I'm multiplying and I have the same base? I just add my exponents. So this is really x times e to the x plus 4y. So we can see why it's exactly what we started with. So that's the idea with this. So to split this up really helps just to make things less confusing when we actually integrate it. Now, we could keep it in there and integrate it, not a problem, but I think it will cause some extra noise and possibly some errors because of that. So our next step then being, this is the integral from 0 to 1, and then I'm just going to leave that x e to the x out here. And keep this in mind also, that I don't have to worry about any of those constants, and it just works out nice. So here we go. So now we're going to do this integral here, and the derivative of e to the 4y is e to the 4y times the derivative of 4y, which is 4. So what happens here is I end up with a 1/4 to offset that 4, e to the 4y, and then that's going to go from, oops, I didn't put my bounds in here, from 1 to 2. Okay, and then dx. So that's our integration there. So now this is the integral from 0 to 1, x e to the x. And then my upper bound minus my lower bound then is I'm going to pull the 1/4 out as well for this part. So it's a times here. And then this is going to really be e to the 4th times 2 minus e to the 4th times 1 and dx. Okay, so then that results in the integral from 0 to 1. This inside is going to be e to the 8th minus e to the 4th. So I'm going to get, and I'm just going to pull that 1/4 out front altogether. Just get it out of there. Then I have x e to the x. Actually, I should just pull it all out, but I will in a moment. But take a look at this. So this is going to be times e to the 8th minus e to the 4th. And actually, technically, it'll probably be best if I get that out of there, because that's just all a constant there. So I am. So that's going to be the integral of e to the 8th minus e to the 4th over 4, and the integral of x e to the x dx is the integral at hand. And again, that's going to be from 0 to 1. Okay, so now for this integration, we will use the integration by parts, if you remember that. So the idea of the integration by parts is we need a u and a dv. So my u is going to be x because they have that word Lyot. And Lyot means log functions, inverse tangent, algebraic, and algebraic means square root functions, polynomials, variables I add and subtract together or divide or other operations. And then we have trig functions and exponentials. And this just gives us the order of what we should pick for u. So when I look at this, and it's by multiplication this happens. So when I look at this, there's my times there. So my polynomial should be my Lyot, so to speak, and that's the a. And the a comes before the exponential. So therefore, my u is then going to be the x. And my dv is going to be the ex dx. And then when I integrate this here, because I need to get a v, not dv, so then v is going to equal e to the x. And I have to differentiate this u equals x here. So this is going to be du equals dx, because it's going to be 1 dx, so just dx. So now this integration by parts then equals e to the 8th minus e to the 4th. I'm just bringing everything along for the ride because I don't want to lose anything. And this part then becomes u times v, that's the formula. So my u times v is going to be x e to the x minus the integral of v du. So my v is e to the x, and my du is dx. And remember, this is going to be from 0 to 1, and this also is going to be from 0 to 1. So each piece has to have that parameter of 0 to 1. Many times people look at the first part here and realize, what do I do with that? It seems confusing. When I integrate it, it's from 0 to 1. So now this equals e to the 8th minus e to the 4th over 4. And this, when I plug in the first part, my 1 in for x is just going to be e. And then when I plug in 0 here for both my x's there, that's going to be 0. So my fundamental theorem of calculus tells me that I'm going to get e minus 0. So I'm just going to get an e for that first piece. So I'm just going to write an e here. Okay, now then for this second piece now, I'm going to integrate that. So the integral, and I'm going to put my minus in there as well, the integral of e to the x dx is just e to the x. So e to the x from 0 to 1. So then when I plug in 1, I get e. When I plug in 0, I get 1. So now that's going to result in, let me keep this here too. So that equals e to the 8th minus e to the 4th over 4. And this is going to be inside e minus, and then in here I get an e minus 1. And that's what I end up with. Oops, excuse me. And I should have made it just a little smaller. So then I can say that this equals, now what's going to happen is these e's are going to cancel, and that's going to become a plus 1 because I'm going to distribute the negative through. So then I get e to the 8th minus e to the 4th over 4, and this is going to be times 1. And that equals then e to the 8th, let me fix my 8, it kind of looks like a 9, minus e to the 4 over 4. And there's our answer for this integral, this double integral.